Hello everyone, welcome to our LoRa Alliance webinar today. We are going to get started right on time here. My name is Megan Leonard and I am on the LoRa Alliance marketing team, and I have just a couple housekeeping notes before our speaker, Olivier Seller, will begin today's presentation. So again, welcome to the second webinar in our technical webinar series featuring LoRaWAN. If you missed the first webinar on March 30th, it is now available on demand, which you will see in the resources box on your screen. Not to worry if you missed the first webinar, as today's content is not dependent on the first one, but in case you'd like to go back and watch it. So for those housekeeping notes, first you can see there's a lot of information included on your webinar console on your screen. You can move these boxes around as you need. You can minimize or maximize the different boxes and really customize your experience as needed. For technical issues, such as if you see your video or your audio is lagging or behind, refreshing your screen typically fixes any lagging issues, and really most issues if you do experience any. There's also a toolbar along the bottom of your screen there, and pressing the help box, which is the box with the question mark in it, will take you to information on how to solve most technical issues. On your screen, you can see there's also a box labeled questions, where you can submit your questions for Olivier throughout the webcast, and he will be answering questions at the very end. Lastly, an on-demand version of this webcast will be available within 24 hours, and you can access it using the same link you used to access today's webinar. So enough of those notes, and with that, I will gladly hand off to today's speaker to introduce himself. Olivier, please go ahead.
Thank you, Megan. Hello, everyone. Thank you for joining today. So I am Olivier Seller. I work for Semtech as a technical fellow here, and I'm mostly responsible for physical layer design, including working on LR-FHSS. I'm also the technical committee, the vice chair of the technical committee of the LoRa Alliance. So today, we're going to talk solely on long-range frequency hopping spread spectrum modulation. And here's the agenda. The first part is to summarize the properties of LR-FHSS and its advantages over the LoRa modulation, and to further state them already. It's longer range in FCC regions, first very important property of LR-FHSS, and second is higher capacity of a single gateway. Then I will explain how LR-FHSS is integrated within LoRaWAN, how to operate LR-FHSS with LoRaWAN. And then we go to modulation details, first with spectrograms, time frequency representation of the modulation to explain the details of it. Then some simulation results on uplink capacity with LR-FHSS, which is of course one of its strengths. So how far can we go as capacity is concerned? And last, a very important property also of LR-FHSS, which is its robustness to Doppler, which fits low Earth orbit LEO satellite applications. So first, the properties of LR-FHSS modulation. So this is a GMSK modulation, Gaussian minimum shift keying, at 488 samples per second. Since this is a low data rate, it has long range, and the link budget similar to LoRa SF11, SF12, for those who are familiar with the LoRa modulation. The data rates are either 162 or 325 bits per second, thanks to conventional encoding with rate 1/3 or 2/3, and that forward error correction is there to bring interference robustness and also robustness against collision between two LR-FHSS transmission. The signaling of the GMSK modulation is differential, and it's on purpose differential to support high mobility, high speeds, high variation of the Doppler shift and high Doppler rate as a consequence. This modulation can be received with any V2 gateway in the V2 reference design gateway from Semtech. It's uplink only, so you can only transmit from an end device to a gateway with LR-FHSS, and there is no TDOA, there is no timestamp, no accurate timestamp on this waveform because the bandwidth is too small for that. So the main advantages of LR-FHSS over the LoRa modulation are first, it's longer range in FCC region. Because LR-FHSS, the frequency hopping part, is aligned to the definition and rules of frequency hopping under FCC regulation. We can transmit longer frames, longer payloads, and also at a lower data rate. With LoRa, the lowest data rate is SF10, and if you need more than 11 bytes, you're actually limited to SF9. So that's not the same sensitivity as LR-FHSS. So first thing, longer range, longer payloads in FCC region. And the second important advantage is that the spectral efficiency, when used combined with the LoRaWAN protocol, which is a random access protocol, is better with LR-FHSS for the low data rate. LoRa is not bad at spectral efficiency, but that's only when high data rates are used. So LR-FHSS performs very well when few gateways receive many low data rate, therefore many hard-to-reach end devices, and which makes it very well suited to communication towards satellites, because that's the extreme case of having few gateways talking to many, many end devices. So now the integration with LoRaWAN. So first of all, this is an optional data rate. It's defined in the regional parameters document. And here I give two examples of regions. There are 3 regions supported so far. More are coming. The first 3 regions supported are US 915, Australia 915, where the hopping steps are 25.4 kilohertz, and that makes it suitable for 1 watt operation, 30 dBm, because the channels are spaced by more than 25 kilohertz under the FCC definition, and there are more than 50 channels. And that's why we are using a bandwidth of 1.5 or so megahertz for this US region. In the US region, we have defined two data rates, 5 and 6, which the first one is coding rate 1/3, meaning 160 bits per second, and the second one is data rate 6, 320 bits per second. In the Europe, here is the EU 868 megahertz region. There are 4 data rates defined. These data rates corresponds to 2 different bandwidth, 2 different size of channels, either 200 or 400. So 200 is slightly higher than 137 that you see here, and 400 is also higher than the 336 kilohertz that you see here. But that's because of the uncertainty in the transmit frequency due to the crystal error, to the crystal inaccuracy. The end device transmits within 137, but needs to be received within 200. The reception has to be wider than the transmission because of the frequency uncertainty. So it's really 200 or 400 kilohertz channels that we define here, either at 160 again and 320 bits per second. So that is the definition of the data rate. So first of all, this is an optional data rate along the other data rate of LoRa and FSK. Now, the setup of the LR-FHSS modulation. First of all, you need to use compatible hardware. Don't worry, there's plenty of compatible hardware. Any second generation LoRa, well, Semtech chip, like the SX1261, SX1262, well, this family can transmit LR-FHSS. Third generation chips, like the LR1110, also can transmit this modulation. And again, any V2 gateway or an equivalent gateway can receive the modulation. So the end device may be activated by personalization, or it may use over-the-air activation and applies the join procedure with join request and join accept. The join request and join accept have to be performed with a LoRa data rate. But it can be an ABP or an over-the-air activated device. Then to further set up the system, it depends on which region you are operating in. If you're operating in Europe, you need to create a dedicated channel for LR-FHSS using the new channel request command, MAC command. That command includes the center frequency on the channel and will tell from the data rate whether this channel is 200 kHz or 400 kHz. So that's why there are 4 data rates, 8, 9, or 10, 11. And for the other regions that support LR-FHSS so far, the fixed channel plans, as we call them, in the US and also in Australia, it's the same. Channels 64 to 71 are defined for LR-FHSS or LoRa. So it's just that the data rates are not exactly the same number. So in the US, it's data rate 5 or 6 for LR-FHSS, or data rate 4 for LoRa 500 kHz SF8. And in Australia, in AU 915, it's not only in Australia, of course, it's also all South America, which uses that. Channels, the same channels, 64 to 71, are defined for LR-FHSS, and it's only DR data rate 7, which is usable. So it's only coding rate 1/3, and that's because we were short on data rate indexes in that region. So now the proper operation. So you operate in a region where the data rates are defined, you have compatible hardware, and you have set up the channel. So how to start using it, LR-FHSS, is from the network server, which is going to send a link adaptive data rate request MAC command, link ADR-REC, to start using it. So in Europe, it's going to be a data rate indication of 8, 9, 10, or 11, consistently with the channel that has been defined. If it's a 200 kHz channel, it has to be 8 or 9, and 400 kHz channel, it has to be 10 or 11. In the US or in AU 915, the data rate in the link ADR-REC MAC command should be set to 5 or 6, or 7 in AU 915, and then from the channel mask control set to 4, we indicate that these 8 channels which are suitable for LR-FHSS, which are addressed, and then the channel mask inside that command is going to tell which channel is enabled for LR-FHSS. So now we have our channel enabled. So link ADR MAC command is not only for adaptive data rate enabled end devices. Well, if the end device may turn on or turn off adaptive data rate, if ADR is turned on, then a single data rate, and in that situation it's going to be LR-FHSS data rate, a single data rate is used until another data rate is ordered from the network server. In case the ADR backoff procedure starts, meaning if the end device loses connectivity, well, it will fall back, and that's completely defined in our specification. It will fall back to another data rate. So for instance, in Europe, from DR11, you go down to DR10, and if you still don't have connectivity, you go down to DR0, which is SF12 LoRa. The same applies from DR9 to DR8, then DR0. In the US, it's DR6 to DR5 to DR0, which is SF10 LoRa. And in AU 915, it's DR7, single data rate at LR-FHSS again, to DR0, which is SF12. So that's completely defined if the backoff procedure includes the LR-FHSS data rates. If adaptive data rate is not enabled on the end device, well, the end device still knows that LR-FHSS is available thanks to that link ADR MAC command, which enables this channel with LR-FHSS, and the end device may use any of the active channels with the data rate supported on this channel. So it can mix, it may mix, or it may use only LR-FHSS. It's up to the end device to choose. Again, and that's back to our previous webinar, it's much better to enable adaptive data rate. We strongly recommend to enable adaptive data rate at all times for end devices. Last, for the operation with LR-FHSS, it's only an uplink modulation. So what happens on the downlink? Well, the downlink is just the same as with LoRa uplinks. So the same RX1, RX2 windows with the same delay, with the same channels apply. The RX1 data rate depends on the LR-FHSS coding rate. It depends on the data rate index and also on the RX1 data rate offset for RX1. And for EU 868, it's going to be SF10, 11, or 12, depending on this coding rate and data rate offset. In the US, it's going to be SF7, SF9, 10, 11, 12, and in AU 915, it's only SF11 and 12. So that is the integration of LR-FHSS as an optional data rate into LoRaWAN protocol. So now I'm going to go to modulation details. So here is a spectrogram, so a time frequency representation of the modulation, and you probably have recognized here not LR-FHSS but LoRa frames. So that frame is an SF12 frame. That one is an SF7 frame. You can see it's much shorter and the chirps are much harder to see. And this one is a proper LR-FHSS packet. The three packets carry the same information. So you can see the difference of time on air, and you can also see the difference of frequency span of this different modulation. So for LR-FHSS, this is the occupied bandwidth in the frequency dimension, which is going to be either 137, 336, or 1.5 megahertz. The physical packet is made of redundant headers. The headers give exactly the same information, and the reception of any of these headers is enough to receive completely the frame. Each header is 233 milliseconds. Then there are payload fragments, which also are redundant because here there is a coding rate of 1/3 or 2/3. But if with a coding rate of 1/3, you typically need to receive a little bit more than 1/3 of the fragments to recover the packet. Each fragment is 102 milliseconds long, and everything is modulated at 488 samples per second. So for time on air comparison, you can see that because of the data rate is low, of course the time on air is pretty long, and there is a table which compares the LoRa data rates to the LR-FHSS data rates. We can see here that the limit of 400 milliseconds, which is the dwell time limit for the FCC region, corresponds to 11 bytes at SF10. 11 bytes with LR-FHSS takes 2 seconds, but we are allowed to transmit for 2 seconds because each channel is only occupied for less than, well, either for 233 or 100 or so milliseconds. The packets can be fairly long. At 64 bytes, you can see that it can reach almost 5 seconds. So it's slightly longer than SF12, and it's about the same as SF11. SF11 is not there, but that's to give an idea of the length of the payload. So now is another spectrogram where there are three such LR-FHSS packets. And you can see that they overlap a little bit. So here, these two headers are going to overlap. So they will not be received correctly, probably. There are not so many collisions in the fragments, but there could be some. So in that situation, most likely, the three packets will be detected and demodulated in parallel without a collision, without any problem, without collision. Then the question is, how far can we go? What is the maximum? What is the limit? How many packets could there be on this graph before we experience errors, errors in demodulation or detection? So this plot is answering that question. So I'm going to describe it a little bit more. So on that axis is the system load in %. So the system load represents the proportion of time when there is some activity, some transmission on a given frequency. So a system load of 50% means that on any frequency, on average, 50% of the time, an end device is trying to transmit something. So it's pretty high load. Here is the packet error rate on the y-axis, also expressed in %, so that's clear. So if we look here, we can see that on that blue curve, when the system load is 20%, the packet error rate, meaning the packets which are lost because of collision between packets which try to use the same frequency at the same time, is around 8%. So it's lower than the packet error rate is lower than the load, which is typically not the case in an ALOA system, and that is thanks to frequency hopping. Here, the blue curve is with frequency hopping, so the LR-FHSS as defined. So, and the dotted curve here, the dash curve in blue, corresponds to the performance of LR-FHSS without hopping. So this is, I'm not going to talk anymore about non-hopping LR-FHSS, but it's to show what hopping brings. It really is important to improve the capacity. Because again, on this example at 20% system load, instead of having 7 or 8% packet error rate, if you don't apply hopping, the packet error rate is going to almost triple at 21 or 22% of packets lost due to collision. So the lower the curve, the better, and obviously hopping is better. Then what's the difference between the blue, green, and black curves, or what we do with interference and self-system collisions? With the blue curve, we do nothing. If there is a collision, so if on a fragment there is information or there is energy from another packet, we just take the hit and don't tell the decoder, the Viterbi decoder, to do anything special. So there's going to be interference. The decoder is not going to be aware of it, and too much noise is going to enter the receiver, and eventually we will get errors. The black curve here corresponds to a case where we can first estimate perfectly the interferences. So we know which fragment is and when a fragment is going to be interfered, and we also know exactly the with which power, which is the interfering power for that fragment. And we tell the decoder, the conventional decoder, the Viterbi decoder, that this fragment is bad or is not so good. So we weight it also optimally before it's being decoded. So it's not as complex as successive interference constellation. That's not what we're doing here. We are just estimating the interference perfectly and then apply the optimum weighting at the input of the decoder. So for those who know a little bit more about forward error correction, it's about weighting each log likelihood ratio by the estimated, so the perfectly estimated signal to interference plus noise ratio. So that's the black curve. And you see that, so that's the theoretical limit for a reasonable receiver, which is just estimating and coping with interferences. The green curve is basically a realistic implementation, a practical implementation of the same principle. So so today we are here at the green, and we will go down probably as close as we can to the black curve. We see here that the theoretical limit, if we consider that a 10% packet error rate is acceptable, is 50% system load. So it means that on each channel, on each frequency, sorry, it's not really a channel, frequency is a bit arbitrary. On each frequency, on average, 50% of the time, there is one LR-FHSS packet being transmitted. So that's, and this corresponds, this 50% load corresponds to 1,000 simultaneous transmission per megahertz. Say you have 1.5 megahertz in a US or AU region, it means 1,000 simultaneous transmission, 1,500 simultaneous transmissions. The reality on the V2 gateways is that we are today limited by the digital signal processing, digital signal processor, and also a little bit by the implementation, and the limit is around 100 simultaneous reception. So we will not be able to reach this theoretical limit, but we still have a nice margin with 100 parallel receptions. So that was the capacity for a single gateway. Here is just an example of what the spectrum looks like when the load is 10%. So again, 10% is here. It means that if we detect interference and manage them, there is no error. If we don't do anything, the packet error rate is going to be around 2%. So it's pretty low. Of course, it's because it's not a human which is doing that, because we don't see anything, honestly. It's it's the gateway which is going to sort out everything. But it looks crowded, I think. You can find the same as me. Here is now a zoom on the same example of 10% load, where we can see a little bit more the collisions. So here there is one collision, here there is one, and you can see that there is a collision because there is a little bit of ripple in the signal amplitude, and that's because of constructive and destructive interference which alternate. The GMSK is constant envelope modulation, therefore the signal level is constant, but it's only when two such constant signals collide, because they don't have the same frequency exactly, well, it starts to make waves of amplitude, and we see these waves. We also see waves in the frequency direction, up and down here, and that's basically the modulation. GMSK is a frequency shift keying modulation, which is coherent, but it's basically a frequency modulation. Therefore, bit equal to 1 corresponds to a positive deviation of the frequency, and a bit equal to 0, a negative deviation of the frequency. So with LR-FHSS, this is differential, so it's a little bit more complex, but that's the idea. We see the modulation here with variations of the frequency. A summary and a comparison of the single gateway capacity between LoRa, here with high proportion of SF7, so high data rate, so dense deployment, or only SF12 LoRa compared to LR-FHSS. Maybe this 125 kHz channel, that's a bit of a waste for LR-FHSS. And let's look at this one, 1.5 MHz channel. So it's comparable to 8 channels of LoRa. If we have a high proportion of SF7 devices, we get roughly a little bit more than 1 million uplinks per day per gateway. If we are only at SF12, then this goes down to 40,000 uplinks per day. So indeed, there is some limitation in the capacity at SF12. And this is solved completely by LR-FHSS, which offers a little bit more than 1 million uplinks per day in the current implementation, and with a theoretical limit at almost 20 million uplinks per day in these 1.5 MHz channels. So now I'm going to show something slightly different on capacity. Instead of looking at the single gateway capacity, we simulate here a network capacity. And what happens when the network gets denser and denser? So here on this axis is the gateway density, expressed as number of gateways per square kilometer. So here it's 1 gateway per square kilometer, here it's 2 gateways per square kilometer, etc. And on the y-axis, it's the capacity, but it's not the capacity of the entire network, nor the capacity per area, it's the capacity per gateway. So the total capacity, as we increase the gateway density, is of course going to increase also. But what we see as a decrease is with LR-FHSS is the capacity per gateway. And why is this going down? Well, it's because in such a network, LR-FHSS will be deployed on the same frequencies for all gateways. Therefore, they will overhear the other packets. So every gateway will try to receive the same packets. So it's a little bit of waste of resources, and which is why the capacity per gateway is going to decrease. But it starts from a very, very high value. The opposite happens for LoRa. When the gateway density is small, all end devices need to use SF12, therefore the capacity is fairly low. But as we increase the density, the capacity per gateway increases thanks to adaptive data rate, because gateways, well, end devices start to use more and more the high data rates. And then at some point, there is the same effect of overhearing of macro diversity, which is equivalent, which decreases a little bit, and then it's flattish. And so when the gateway density is small, is low, LR-FHSS is much better. And when the gateway density is high, actually LoRa is better, and it means that LR-FHSS doesn't bring anything. So the conclusion is simple. Use LR-FHSS when you don't have so many gateways. And of course, the extreme case of that is satellites. And good news, for one particular kind of satellites, the low Earth orbit satellites, the one which are between 500 kilometers altitude and I think 800 kilometers high from the ground, they spin pretty fast, meaning that their speed is high and their relative speed to the ground is also high. And as a consequence, there is a strong Doppler shift, a strong variation of the frequency of the received packet. And not only does the frequency is shifted, but that shift is not constant. And really, that is the thing which is difficult to fight. It's the fact that the Doppler shift is not constant. It's called Doppler rate, and it can be as high as 250 hertz per second. And since a packet can be 4 seconds long, for instance, it means that the shift over a packet is going to be 1 kilohertz. 1 kilohertz, it's twice the modulation bandwidth. So you start a packet with some frequency synchronization, but you need to track it pretty well because that frequency synchronization is going to be completely wrong. It's going to be wrong by twice the bandwidth. So if you start to receive on a frequency, at the end of the packet, it's a completely different frequency that you need to receive. So there is a tracking challenge here, but thanks to the differential modulation, we can stand, well, LR-FHSS can stand that Doppler rate with a minimum sensitivity loss. So as a conclusion, I would like you to take away this benefits of LR-FHSS. So it's a new uplink data rate well integrated with LoRaWAN. The main advantages are longer range for the US FCC regions, or AU, South America, which allows lower data rate, therefore longer range, and also the possibility to use 1 watt. It's compliant with the FCC definition of frequency hopping. The second advantage is high capacity for gateways which need to talk to or receive many hard-to-reach devices, many high-link margin devices. And last but not least, LR-FHSS tolerates a very high Doppler rate, which makes it compatible with LEO satellites, with LEO satellite gateways. So this ends this part of the webinar, and you can, I see that you have started already, you can continue ask questions either here for feedback and suggestions, and the Q&A also in the Q&A box. And before we go to the Q&A, I hand it over to Megan, who has also concluding remarks.
Great. So much, Olivier. Such a great presentation. We have just a couple final remarks before we head into that Q&A section. So let me just jump into those. So be sure to register for our final webinar in this technical series on May 10th. There is a link to register in that box labeled resources on your screen if you have not registered for this next one yet already. And also keep an eye out for future technical webinars that we'll be hosting. We will be continuing this series throughout the year, and we hope to see you on the next one on May 10th. If you're not already a LoRa Alliance member and are interested in becoming a LoRa Alliance member, please reach out to our LoRa Alliance team, and we'll be happy to discuss with you the numerous benefits and marketing opportunities you receive as a member. So click the LoRa Alliance membership box on your screen to learn more. Lastly, we invite you all, members and non-members, to please join us for the LoRaWAN World Expo event happening this July in Paris. This is the official LoRaWAN event of the year and open to the entire ecosystem. We will have 2 days of great keynotes, sessions, panels, a full exhibition floor, networking parties, and so much more. You can scan the QR code to visit the event website to learn more and register, or click the box with this image on your webinar console to be taken directly to the event website. We hope to see you all there. It will be a fantastic event and a lovely time in Paris during the summer. All right, now it is time for the question and answer session. Please make sure you are using that questions box, as Olivier said, to submit your questions. We do have Dave Kenjel from Senate, and who is also a LoRa Alliance board member, joining in to help moderate the questions. So give us a moment here, we'll get Dave connected, and then we will begin. Thanks, everyone.
Thank you, Megan. This is Dave Shundle here with Olivier Seller to take your questions and hopefully provide some answers. We do have quite a few questions that came in during the course of the webinar, so we'll start with those, and again, feel free to add your questions as we go along. We'll start with the question from Polo. The question is, the communication distance between the gateway and LR-FHSS devices could be, let's say, in urban areas. So the general guiding principle here is that the link budget is roughly the same between the highest spreading factor LoRa modulation and the LR-FHSS communications. Keep in mind that you have two additional factors here. So one of them, as Olivier went through in quite a lot of detail, was the additional capacity that a single gateway can provide in those scenarios. And that was really one of the overriding benefits in the more bandwidth constrained regions like Europe. The other one is the ability to transmit more information while still complying with the regulations in the Americas. So this allows at the highest equivalent link budgets that you're able to communicate more information, which is again very important. And also in those regions, you're able to take advantage of 1 watt transmitters while still remaining compliant using that, using this new modulation technique. The second question comes from Olivier around gateway hardware, which is required to support LR-FHSS. Olivier, you want to take that question?
Yeah, sure. So which gateway is required to support it? So it's only the V2 reference design with additional DSPs, which today can receive LR-FHSS. So SX1302, SX1303 cannot on their own. They would need also an additional DSP. And of course, you can imagine that Semtech is working on a roadmap, but today it's only supported with a DSP.
Thank you. Fabio asks, why is LR-FHSS only available in the uplink? Olivier, can you help us with that?
Yes, so it's because, I mean, as I just said, we need a DSP to receive it because it's complex to receive. You need to, the frequency is not well defined, so you need to define many channels to try to detect the signal, and then they modulate it. Therefore, it's a complexity issue. That's why it's only available in the uplink. You need a gateway with quite massive DSP capabilities to be able and to detect specifically to detect the LR-FHSS packets.
Well, thank you. And maybe you can answer this next one, kind of a technical question from Olivier around potentially processing the LR-FHSS components centrally as opposed to on an individual gateway.
So that's a good idea. That's I mean, the cellular world is doing this. They're doing macro diversity at the physical layer. So fragments or even bits can be aggregated together from various gateways. So we could be doing that. But of course, it's a much more complex system. That is certainly possible.
Thank you. Jonas from Mainlink asks, so hi, if we use ADR, will it automatically adjust to use LoRa or LR-FHSS having the gateway density in mind? So certainly that's a function of the way that the network server is configured to take advantage of that. And obviously that requires gateways that can process it and knowledge that the end device itself also supports the new modulation technique. But in that sort of environment, that's exactly what we would imagine a well-behaved network server would do, would be to automatically use ADR to provision the device to use that modulation when it's the right thing to do, either to provide that extra reach or that extra capacity in a low density network, and then to migrate it over to LoRa modulations when the RF parameters indicate that that's the correct thing to do. All right, Eric asks, so you mentioned there is a limit on simultaneous receptions per gateway limited by the DSP power. Is there a difference in the number of simultaneous receptions regarding gateways using the different 1301 or 1302 chipsets?
So no, there's no difference because the reception of LR-FHSS is not achieved within these chips, within the SX1301 nor SX1302. It's achieved in a DSP, which is separated. So to have more than 100 simultaneous reception, you can use, and some companies that build gateways, including for space, put bigger DSPs and manage to increase that number.
So Matthew asks, you mentioned LR-FHSS loses network efficiency compared to LoRaWAN in crowded areas. Where is that threshold, quantity of end devices? I'll take a stab at answering this, and Olivier, you can correct me as I go off course. So I think that the interesting concern is slightly less than the density of the end devices, but the density of the network behind them. So what Olivier was showing really was that in a dense network design, we have lots of gateways, that you will have lots of overhearing because LR-FHSS propagates so well. Again, in the ADR environment, the network should be automatically re-provisioning those devices to be using LoRa in that environment. So I think it's less of a question of end device density and really more of a question of network density that will drive that optimization. How to do it, Olivier?
Absolutely. I have nothing to add. Exactly. It's about gateway density. Maybe I was not so clear on the graph, but that's correct. Gateway density is the driver.
So Ramez asks, do we already have certified devices with the LR-FHSS data rates? I think I can answer this one. I think we are early in the phase yet, so we only released the regional parameter specification that included the data rates early last year. So I think the certification process is now just catching up with that. I believe that the next round of certification test will be able to certify LR-FHSS devices. Matthew asks, can you talk some more on the basics of the satellite connection, common protocols, recommended third parties, and connection methods? So I think in the context of the LoRa Alliance, we'll stay away from recommending third parties, but certainly maybe Olivier, you have a few more comments to add on the satellite technology or techniques.
Well, not so much. Indeed, we can't give recommendation. It's going to use LoRaWAN. It's going to use uplink for sure. It might use downlink, but it's down to the different satellite operators to provide or not provide downlink. Satellite can be in combination with terrestrial network, and that's a very useful feature. The same modulation, the same packets can be sent and received either by satellite or by a terrestrial gateway. So networks can cooperate from the protocol level and also using this LR-FHSS modulation, which is common ground and satellite.
Thank you. Itano asks, could you explain what impact LR-FHSS modulation has on layer 3 from the network server? So OSI models always get a little fuzzy when you get outside of layer 1, 2, and 3. So layer 3 is kind of the bridge between the network server and the application server, at least in my mind. So the LR-FHSS is really a physical layer, a layer 1 component to the overall system. And you've seen the very small adaptations that were required in the regional parameters specification to identify these new data rates. So that's a very, very minor impact to layer 2. What the real impact is beyond layer 2 has to do with the fact that you have the potential opportunity in dwell time constrained regions to encode more information in that data frame. So now you will have a longer frames on air, but you can have that ability to send more data in those messages, which may open up your application layer 2 technology, layer 3 technologies that you're using to additional techniques that might not have been available to you when you were constrained just to say 11 bytes as application payload. Paul asks, which component actually assembles the received fragments? Is it the LoRa gateway chipset or the packet forwarder? Thanks. And I think I've heard enough now that I can answer this question too. So I think it's the DSPs that are on the part of the chipset package that are actually doing that reassembly. The packet forwarder really takes the demodulated complete frame and it delivers that via a protocol, typically IP-based protocol, up towards the network server.
Yeah, exactly. And back to the question, an earlier question from Olivier, that could happen. That assembly of the fragments could happen in the network server or in the server from many gateways if we were to combine the diversity in a central manner. But that's not what we do today. We assemble that in the DSP. So I think the final question we have right now, so again, feel free to add some additional questions to the Q&A box. The final question is from Navendra. If the higher gateway density limits of the LR-FHSS performance limits the performance of LR-FHSS, is it right to say that LR-FHSS won't really be a help for capacity improvements in existing dense deployments? But for the use case that have low densities like agriculture, other than satellite, it can support more end devices than LoRaWAN can. Can you list a few more? So I think that there's the way that I think about this as an operator is that there's a balance point that you're looking to have. So in very, very dense LoRa modulation environments, you're going to be tuning all those end devices down to very low spreading factors, very high data rates, even potentially dropping the transmit powers down to minimize the overhearing, and that's really going to drive. So again, you have a very, very dense gateway deployment, and think of set-top boxes in an apartment building or something like that. And so LR-FHSS really isn't going to provide a particular benefit in that use case. However, in more traditional outdoor networks, where you still have the challenge of providing coverage, that's really where you get to bring these two other behavior benefits to bear. So, which are the increased capacity of an individual gateway, as well as the ability in dwell time constrained regions, to send those longer frames. So we see this, I think, generally speaking, there's a lot of anticipation that in a lot of the utility applications for water metering, gas metering, these sorts of things, that this is a really powerful tool that will help us solve both of those problems. Those are very, very dense end device deployments that are always kind of coverage challenged. Right, just got a whole nother set of questions in here. Let me grab some. So kind of going from reverse, Paul asks, what parameters can we configure for LR-FHSS, like max on airtime? Thanks. So the configuration of the modulation is done through the application of the data rate at the network server. So most network servers will give you some control over which data rates are acceptable for the end device to use, and that would be one control. A control specifically like max airtime is really going to be driven more by the implementation on the end device, and that may also then be constrained by duty cycle limitations that might be applied by the network server as well. So
Marcus asks, is the benefit of this feature the same for US 915 and EU 868? If not, what is the difference? So I think we talked about this a couple of times, but again, at least in my mind, the primary driver in EU 868 really has been around increasing the capacity of those individual gateways. So very, very dense deployments of end devices, sparse deployments of networks really lets you kind of increase the capacity of those networks significantly, as Olivier went through. In the US 915 region and the Americas generally, we don't really have as much of a constraint today. We have many more channels, much more bandwidth available in the unlicensed bands to use. However, we are very often constrained by that dwell time limitation that gets us down to 11 bytes in those same kinds of utility-style deployments. You know, dense end devices and sparse network, and so it helps us solve those problems in that way. So slightly different benefit, at least early benefits, I think, for the two different regions based on the technology. Gianni asks, how many fragments over the total fragments of a frame can be lost due to collisions and still be able to recover the whole frame? Olivier, can you?
So if these fragments are lost, completely lost, and you know that they are completely lost, it's about 2/3 when you're using code rate 1/3, because the conventional code is fairly optimum to that respect. So if you lose 2/3 of, basically you lose all the redundancy, but you have enough to recover your initial information. So it's a little bit less than 2/3, the answer, and a little bit less than 1/3 when the coding rate is 2/3.
Just running through here some of these. So I think there were a couple of questions, and these may have been answered in the chat already around, Mavendra asks, is the documentation, so what's been available in the slides here, and maybe some of the backing information around the studies that you and simulations that you mentioned, Olivier, will those be, are those available someplace, and will that be communicated to the webinar team?
So there will be some communication, but not immediately. I mean, of course, the slides are available, but the details of the modulation, we are going to publish with a research team in France some results, and there will be more details and more information on this kind of simulation for capacity.
So we have a question from Gianna. Does ADR make sense for low Earth orbit communications with channels that change very fast? I think that's a very good question. It's certainly, I think it's early days in terms of our understanding of exactly how those optimizations will make sense. I think at least in early days, I would guess that in the LEO environment, if it's pure satellite communications, that we won't probably be doing a lot of dynamic data rate adaptations to those. As you point out, those satellites are moving very, very quickly, and things are changing probably too rapidly for a typical LoRaWAN ADR communication to make sense. However, that changes when you start considering the hybrid terrestrial satellite networks that Olivier mentioned before, where now you definitely will be using ADR to potentially transition back and forth between areas of terrestrial coverage over back to areas that are purely covered through the satellite connectivity. So a question here from Richard, Mesh Systems. Can you comment on the availability and maturity of end device LoRaWAN stacks with regards to support for LR-FHSS? I'll take a piece of this and then I'll throw it over to Olivier. There was another question earlier too about whether or not LR-FHSS was supported via the LoRa Mac node GitHub implementation as well. So again, I think we've had probably about a year or so where the specifications, the regional framework spec, has been out in the market, published for device makers to take advantage of that. I think the chipsets have been out in the market for quite some time as well. So in terms of the availability of the component pieces, I think that is pretty widely available in the market today. In terms of the actual devices themselves, I think that's an evolving question, and I don't have an answer to that. But Olivier, maybe you can take the question around the back-end support from the GitHub environment on the technology.
So yes, it's available on GitHub. For instance, LoRa MacNode has it. We have pilots with anyone who wants to try and to plan commercial deployments of LR-FHSS. So yes, it's ready and available. Again, from either SX1261 or 2 chips or LR1110 chips. So both can do it, and both have the supporting stacks.
So we have an interesting question from Paul. So can the gateway talk to the satellite via LR-FHSS? I think
why not?
The answer, why not? Of course. It's not a mode of communication that we've defined in the LoRaWAN specifications, but certainly it's a pathway to communicate in that from those two devices. Noelani asks, are you considering changing the acronym LR-FHSS to something more simple to pronounce? I think it's just me who has a problem.
No, but, I mean, you can blame me. But please acknowledge that at least it says what it is. It is very descriptive. And, it's really long range, frequency hopping spread spectrum. But yes, it's difficult to pronounce. That's yeah.
I think we have answered almost all the questions here. There was a few questions on the total bitrate capacity. That's all documented in the LoRaWAN regional parameter specification. So you can see there per region what the different bitrate capabilities are for each one of the different data rates that are defined. A very technical question, just to close it out, maybe, is can LR-FHSS resist to higher Doppler rates such as 600 hertz or 900 hertz? Definitely not me answering this question. So
we don't work that much on these Doppler rates because they are higher than what the LEOsat experience. But I think 600 probably yes, and 900 no. But I think the limit is between 600 and 900, the hard limit. But it's very, I mean, at 500 hertz per second, it means that after 2 seconds of transmission, you have shift by 2. You have shift your carrier by twice the bandwidth. So it starts to be difficult to track. Really not the frequency that you're tracking. The center frequency moves wider than the bandwidth. So that starts to be a challenge, obviously.
So there's maybe we have time for one final question here, and I think this one's for you too, Olivier. I won't read the entire question; that's a bit long. But the nut of the question really is LR-FHSS appropriate for deep indoor penetration, and are there any special considerations considering non-line of sight? So maybe how it behaves in multipath environments is kind of what the question is there.
So with multipath, there is if you're using for instance in the US a 1.5 megahertz channel, you will benefit from a decent amount of frequency diversity. So that's going to help versus multipath. That's less true for Europe, where only 200 and 400 kilohertz channels are defined, and then you will not have that much diversity. So in the US, certainly enough diversity to overcome multipath, thanks to this wide bandwidth of hopping. So diversity means that some channels will be notches of propagation, and some others will be good. And since we can lose, again, 2/3 of the fragments, it's okay. Some fragments will be lost because of multipath, and some will survive, and overall, the packet will be received correctly.
Well, thank you very much for that. And I would like to thank everyone who attended the webinar this morning, this afternoon, this evening for you all. Fantastic attendance, great questions. Thank you very much, Olivier, for the presentation. It was very educational and insightful. Thank you, Megan, for coordinating the webinar as well. And with that, I'd like to say goodbye and thank you all. And please do remember that we have another in the series of webinars that will be coming up in the not too distant future. Please join us again. Thank you.
Thank you, everyone. Thank you, Dave.